Hello, everyone. So today we'll be covering the last part of thermophysics and also the last part of this course. The adiabatic process. So just a little recap. So in the last time, we introduced three elementary quasi-static processes, which are the isothermal, that is T is constant, and isovolumetric, that is to say the volume is constant, and isobaric, that is to say the pressure P is constant. So we've learned about those three elementary quasi-static processes in the last meeting. And today I'm going to talk about the fourth. So adiabatic process is also a quasi-static process, and it's defined as a process in which the gas does not absorb any heat. So it's defined as Q equals to 0. And how do we quantify this process with that definition? So we may recall the first law of thermodynamics, that the heat absorbed is either converted to the work done to the outside of the gas or the internal energy of the gas. So here we have 3/2 for monoatomic gas. And we will see very soon what happens if we're thinking about other kinds of gas where this factor is changed to something else. But just for concreteness, we'll begin with the case where this factor is 3/2. So we have that. And for a adiabatic process, we have Q equals to 0. So this is 0. And we may also recall that by ideal gas law, P equals to nRT over V. So this condition is equivalent to saying that 0 equals to nRT dV over V plus 3/2 nR dt. And we can divide both sides by nRT, and we get 0 equals to dV over V plus 3/2 dt over T. And we can just integral, and then we obtain that some constant, which is essentially the integral constant, equals ln V plus 3/2 ln T. And also recall that, so very generically, alpha times ln x equals ln of x to the alpha. So this is a math formula we introduced or we reviewed last time. So this means this constant is equal to ln of Vt to the 3/2. Oh, and also remember that ln x plus ln y equals ln xy. And in other words, this means that Vt to the 3/2 is a constant. Since the ln of that is a constant throughout the process, then we see that this number itself should be a constant throughout the process. Yeah, basically this is an extra relation we can have between the macroscopic variables describing the gas when we know that the gas is undergoing some adiabatic process. Or equivalently, since we know V, T, and P are related to each other, so we can make use of the fact that T equals to PV over NR. Then this relation becomes V times PV over NR to the 3 over 2 equals to constant. Which implies P to the 3 over 2 times V equals to 5 over 2 is some constant, which again implies that PV to the 5 over 3 is a constant. How do we get from that? We just take the exponential of the on the two sides. So we take the exponential 5 over 3. So this thing, so this is put into here, and 2 over 3. Yeah. So we look at this and take exponential to 3 over 2, and we get this one. So we have got two equivalent descriptions of an adiabatic process. So usually people will describe the relation as PV to the gamma equals to constant, where gamma equals to, so gamma is actually some value that depends on the type of the gas. And we've shown that for monoatomic gas, gamma equals to 5 over 3. But more generically, we can establish some relation between the gamma here and the coefficient there in the internal energy. So when the internal energy is 3 over 2 nRT, we've seen that gamma equals to 5 over 3. And when U is 5 over 2 nRT, then from a very similar derivation, we can get that gamma is 7 over 5. And for U equals to 7 over 2 nRT, we will get gamma equals to 9 over 7. So this is how we relate the gamma to the coefficients here. Yeah, and after looking at the past finals, I think I need to make some further remark about the internal energy. So I think I need to explain where those factors come from. So the fact is that the internal energy can be written as d over 2 nRT, where d is the degree of freedom. of molecule of the molecule making up the gas. So what does it mean? So D is actually, so the degree of freedom actually refers to describe the status of a single molecule making up the gas. How many variables do we need? So for example, for monoatomic gas, so we can describe its position by x, y, z. So those are 3 variables. And we know that for a monoatomic gas, so the molecule is just an atom. And to specify an atom, we just need to specify where it is. So that's why we only need those 3 variables to describe it. That means D equals to 3. And as a result, the internal energy is just 3/2 nRT. But for diatomic gas, the things get more complicated. So at low temperature, then we can approximate the diatomic molecule by a simple model where there's a rod on the 2 ends of which is connected the 2 atoms. And how do we specify the rod? So how do we specify the status of the rod? We know we can describe its center by x, y, z. And in addition, we need to describe the angle of that rod. So that actually contains 2 degrees of freedom because, so imagine a rod in 3 dimensions. It could rotate in this way, but it could also rotate. So imagine that there is a plane and the rod could also rotate in this way. So yeah, so if you look at a pencil and you hold it and you study to how many angles it, like if you study in which directions it could rotate, you will see that there are actually 2 angles by which you can describe its position. So those angles we call theta and phi. There are 2 additional angles. So therefore, we need x, y, z, and theta and phi. So that's why we have U equals to 5/2 nRT. And that holds for oxygen or hydrogen or nitrogen, as long as the temperature is not that high. And that holds for room temperature as well. But when the temperature goes even higher, we have a subtlety here. So at high temperature, and that temperature is usually a lot larger than the room temperature. So we're talking about, we can describe the diatomic molecule by a rod, but at high temperature, that picture is too simplified. And in fact, we have to take account of the radial movement of those atoms. And therefore, the rod cannot be the rod anymore. It has to be a spring. And in that case, there are extra degrees of freedom because the 2 atoms could move, like they could oscillate on the 2 ends. They could oscillate in the radial direction. And this oscillation, surprisingly, this introduces 2 extra degrees of freedom. Therefore, in addition to the x, y, z, and theta phi for the low temperature case, we have to take account of 2 extra degrees of freedom. And that means d equals to 7 for the diatomic molecule at high temperature. And therefore, U equals to 7/2 nRT. And the picture here is that at low temperature, it's just a rod, but at higher temperature, you can imagine that you can think in this way that the oscillation gets excited at high temperature. Because at high temperature, you can imagine there's more energy. And yeah, that energy just excites the oscillation. We have 2 more degrees of freedom, and we have this one instead. Yeah, I think those are just some backgrounds underlying the expression for the internal energy, and there's some physics that are good to know. Yeah, that's why I'm talking about that. Then we'll move on to another topic. And I think this is a topic that usually is there after one introduces the adiabatic process. That is called the Carnot cycle. So Carnot is a French guy. So he's a French guy. So I think the T is silent. And this is a special cycle that is described in this way. So here's the definition of the cycle. And we'll just describe that on the PV diagram. So it just involves some gas undergoing some quasi-static process. And the process is as follows. So from point 1 to point 2, this is isothermal, and the temperature is TA, or let me call that the higher temperature TH. And from 2 to 3, the gas undergoes some adiabatic process. And from 3 to 4, again, the process is isothermal with some temperature T low. And again, from 4 to 1 is adiabatic. So let me write it out. So 1 to 2 is isothermal at temperature T higher, and 3 to 4 is isothermal at temperature T low, and for the processes 2 to 3 and 4 to 1, so this is L. So for those two, it's adiabatic. So why do we have? So why do we need to study this cycle? So this cycle characterizes a heat machine. It is a machine that works between some higher temperature and the lower temperature. So imagine that there's some machine that absorbs heat. And basically, the machine contains some gas, and the gas absorbs heat from a large reservoir at high temperature TH. And then the temperature decreases and it does some work. And then the temperature decreases to some lower temperature TL. Yeah, and then the machine is just connected to a reservoir at lower temperature TL. and it restores to the initial state, and it goes back. So basically, the machine absorbs heat from the higher heat bath and converts that to work. And a key question is, what's the efficiency of that conversion? So what's the maximal efficiency in which we can convert the heat to the work? So the question is about efficiency. And we will see soon that this is a very simplified version, or this is a very simplified model in which we can study the efficiency of a heat machine. And calculation is not that involving, and I'll go over that from now on. So we see that the first question is how much heat is absorbed by the machine. So we know that for 4-to-1 and 2-to-3, the process is adiabatic. So it doesn't absorb or release any heat in those processes. So as for the heat absorbed, we just need to think about this process. Since in this process, we know that the machine is releasing some heat to the reservoir. So, but we're caring about the heat absorbed when we talk about efficiency. So we first need to figure out the heat. So we know that from 1 to 2, it's an isothermal process. So since the temperature stays constant, then the internal energy doesn't change. So we know that the energy the gas absorbed should be equal to the energy, or should be equal to the work it does to the outside. Yeah, so we have that because the change in internal energy is 0 because the T is constant. The temperature is constant. So what is that work? We have worked out the expression for the work for the isothermal process. So it's just nRTH ln V2 over V1, where intuitively V2 denotes the volume of the gas at point 2, and V1 denotes the volume of the gas at point 1. And then so that's the heat absorbed. So what about the work done by the gas? Well, in the last meeting, we talked about the work done by the gas is just the area of, it's just this area. But practically, this one is not easy to compute. So instead, we will work on the work done during those processes one by one. So let's look at 2 to 3. So we know 2 to 3 is an adiabatic process. So Q equals to 0. Therefore, the work, so recall that dQ equals to du plus PdV, where PdV is the work. So this is the first law of thermodynamics. And in this way, we know that the work done from 2 to 3 plus the increase in the internal energy. Yeah, just for simplicity, we assume that the gas is helium. But we will assume that this result can be generalized to any kind of gas. So the increase in internal energy is final minus initial, so T3 minus T2. We know this is 0. So W2 to 3 equals to 3 over 2 NR T2 minus T3. So for 3 to 4, we know the work done is by, it's just NRTL. We're using the formula we gave during the last meeting. So it's ln of T4 ln of V4 over V3. And 4 to 1 is again adiabatic. So W41 plus 3 over 2 NR T1 minus T4 equals to 0. And that gives W41 equals to minus 3 over 2 NR T1 over T4. And yeah, actually we know what T3 and T2 are. So T3 is just TL, T2 is TH. So just and we know T1 is TH, T4 is TL by definition. T high minus TL. So here it is. And then the work done is just the sum over those works. So before we plug it in, we just observe something. So W23 is this. And W41 is this. So those two, so if we look at those two. Yeah, so these two are just, they just differ by a negative sign. So their sum should cancel. So we know those two cancels. And then we just write together W12 and W34. That is NR TH ln V2 over V1 plus NR TL ln V4 over V3. And so just recall that our goal is to compute the work done by the gas divided by the heat absorbed from the higher energy reservoir, from the higher temperature reservoir. Yeah, so this is Q12. So our goal is to compute this. And so we have this, which is the same as that. This is nice, but we have to deal with this term as well. But it's not that difficult because we just claim something. So we claim that V4 over V3 equals V1 over V2. So why is that the case? So we can actually relate V1 and V4 by this adiabatic process. So by the formula we got from adiabatic process, so we're using this one. Look carefully at this one. And yeah, so by that formula, we know that V1, so through the process, let me make that clear. So from the process 4 to 1, it's adiabatic. So we know V1 times TH to the 3/2 equals V4 times T low to the 3/2. Sorry, the connection doesn't seem great. Yeah, so we look at the PV diagram over the top and see that this is indeed V1 TH to the 3/2 equals to V4 TL 3/2. That's correct. And that just implies V1 over V4 equals to T low 3/2 over T high 3/2. And similarly, we can relate T2 and T3 using this adiabatic process. And you can verify that this just gives this one also equal, this one also equals V2 over V3. Therefore, we have proved that V1 over V2 equals V4 over V3. So with that claim, so with that proof, we know that we can write the work down by NR TH ln V2 over V1 plus NR TL ln V1 over V2 and recall that ln V1 over V2 is just minus ln V2 over V1 using some math formula for math equation for the ln. Therefore, the work done is just R T high minus T low times ln V2 over V1. And finally, we get the work divided by the heat absorbed. So the heat absorbed is this one. So we get just TH, many things cancel. So just TH over minus TL over TH, which is 1 minus TL over TH. And of course, this is smaller than 1 because the energy doesn't come from nowhere. So the heat absorbed, so the maximum work the gas could do is the heat it absorbed from the reservoir of higher temperature. And a remark is that, so this quantity actually gives a higher bound for any heat machine you can, for any heat engine you can have working between two temperatures. So this is the upper bound. This is also why we're studying Carnot cycle, because it's just a cycle that gives the upper bound. And that's why it's interesting. And the fact that this is the upper bound is actually the second law of thermodynamics, which I don't think will be covered in this course. But you might be wondering what's the second law, and this is the second law. So this might be a lot, this law seems to be more weird than the second law of Newton's dynamics. But actually the thing it's describing is quite fundamental. So it's giving you an upper bound for the efficiency you can convert, for the efficiency in which you can convert heat to the work. And this actually has something to do with some arguments involving entropy, which is the another way of saying the second law of thermodynamics. So yeah, this is physically very deep. All right. So here ends the Carnot cycle. I hope that gives you a way of illustrating how we can deal with PV diagrams. And the last thing I'm going to cover is it's actually easier. So it's the thermodynamics of liquid and solid. So we're not dealing with them a lot in this course. So all the models we're taking are very simplified. For example, we're ignoring the change in volume of liquid and solid. A consequence is that since the liquid and solid doesn't change volume in the thermal process, then the heat is absorbed. So that means the liquid and the solid doesn't do any work because the volume doesn't change. So the heat absorbed all converts to the internal energy. And how does the internal energy defined? So that is defined by, so the heat it absorbs all converts to the internal energy. So we can as well define that internal energy equals to mCT. Yeah, I think it's just safer to write everything in terms of the small quantities. So the heat it absorbs, so the heat an object absorbs intuitively should be proportional to the change in the temperature. So this is basically what this equation is saying. And in addition, it's giving us some constant C, which is a specific heat. So that only depends on the material. And the M here is just the mass. This also makes sense because so the larger an object is, the less easier it is to increase the temperature. And yeah, this one we've been talking about is the heat absorbed. And this one is the change in temperature. Yeah, and this is a very important formula. So basically, given any liquid or solid, once you've known the specific heat, so once you know that, and once you know the mass of it, then you know how much temperature it will change. So then you know the change of temperature when that liquid or solid absorbs this much quantity of heat. Yeah, so we've been saying that the specific heat depends on the type of material. And the next question is, so what happens if the type of material changes during the process? This is actually quite common in daily life. For example, when the ice melts, then we know that the ice changes from one type of material, which is a solid, which is ice, to the other type of material, which is a liquid, which is water. So we have to account for that since this is very common in the daily life. So the question is, what if the type of material changes? Example, what happens when ice changes to water? And to answer that question, so basically when ice melts, and this applies quite generally. So whenever a liquid converts to whenever a solid converts to a liquid, or whenever the liquid converts to gas, there is some heat for there needs to be some heat provided for the material so that it could change the status. So in our case, when the ice melts, it absorbs some heat. So the intuition behind that is, so we know ice is a solid. So when it melts, so we know in solid, the atoms are quite confined and the atoms doesn't move around quite much. But when it's melt into liquid, then we know the molecules are moving faster inside the water. So that's why we need some energy input from the outside for the ice to melt. So when the ice melts, it absorbs some heat, and the heat is given by LDM, where the dm is the mass having melt. But intuitively, the more heat the ice absorbs, the more amount of water it will convert to. So this is proportional. So that's why dq is proportional to dm, and dq is the heat absorbed. And this L is called the latent heat. And that's a value which will either be given or is measurable during some experiments. So that latent heat only depends on the process, or only depends on the change. Of the phase of material. So that is another way. So we know, of course, when the ice melts, there is some latent heat. But when steel or iron melts, there's another latent heat, and that heat, of course, is different. So that depends on the material and from which state and to which state the material is switching. So that is what I mean by this comment. Yeah, so I think I've described enough for you to work on the thermodynamics of liquid and solid. And yeah, I think this topic is not that complicated. So it's quite straightforward, and you will see it once you've been working on some problems. So yeah, I refer to the problem 1 of worksheet 15. So I think to master this material, you just need to work on that single problem, and then you will be fine. Yep. All right, so that's all I have for today. And wish you good luck for the final. And I will also be holding remote office hours for the next week. So see you around on Zoom.